catchment is small, you probably expect a smaller flow. Of course, the extension of the catchment is not the only one determinant of the river flow. There are other determinants: rainfall, infiltration, evapotranspiration, vegetation, human impact. But the catchment area is a very impacting determinant. Okay, how large is a catchment? I showed you an example just at the beginning of the lecture, 6 square kilometers. 6 square kilometers is considered to be a very small catchment, very small. There is an interesting list in Wikipedia of the largest catchments in the world. And here there is a map, which is nice. And keep in mind that I already mentioned to you, hydrology has been always approached at the local level. So basically one has to design in a given place and he looks at the given river at the given catchment and nothing else. We should stop with this view. Hydrology should be looked at with a global vision, because if you have a global vision, you can better understand the local conditions. So every time that you really have the opportunity to observe global, take this opportunity. So in this case, I could skip to show you this picture. But I think it's important that you look at the global vision, so you understand what is really a large catchment. Okay? So basically, this is basically, you know, with the same color, they identify the contributing catchments to the Atlantic Ocean. So Atlantic Ocean is written in green, and you see the contributing area to the Atlantic Ocean in green. And here there is, it's difficult to read in yellow, there is a, let me see. Okay, it is the American Mediterranean Sea, basically this portion of sea. You may say that it's part of the Atlantic Ocean, but you see that it's almost closed. So they call it the American Mediterranean Sea. And this is the drainage basin. You see the drainage basin of the Mediterranean Sea. It is much extended. It includes the Nile River, so a large part of Africa. And also here there are markers for each individual catchment. This is the Amazon River. And if we look at, guess what is the largest catchment in the world? Here there is a list. And the largest one, it's, yeah, let me see. This is, first of all, you see the contributing area to each ocean. But then you see the Amazon River. It is the largest river, and the area is, you see the basin area in square kilometers of the Amazon River is in kilometers squared 6 million. This is 6 million. 6 million. 144,000 about of square kilometers. The Po River is 70,000 square kilometers, to give you an idea. So the Amazon River is, and basically if you browse down, you get to the smaller and smaller rivers. And you get to up to, or down to sizes that are comparable to that of the Po River. The Po River is not listed here, but should be about here, in between here. Okay, let's go back. So we define the catchment, and then we can speak about models for estimating the peak river flow. And so we get now to the definition of the models. I'm taking a break in 10 minutes from now, okay? And basically, now let's go to the models, and this is the technical part that is much interesting for us. And look, we didn't speak about theory so far. I didn't mention theory. So the models, first of all, let me say that the classic approach to education in hydrology used still uses to divide estimation models in categories. So for the case of the estimation of the peak river flow, I remind you that we are focusing our attention to the estimation of the peak river flow. We'll talk later about the hydrograph. So we are interested now in getting a number. And this number refers to a river cross-section, which in turn refers to a catchment, and this number refers to a return period. The return period is assigned by law, the site usually is assigned by our client, so now we have this information we already have, and now we have to look at the models. I said, the classic approach in hydrology to the estimation of the peak river flow usually divided the estimation models in two main categories. And these two categories are the probabilistic models, which refer to statistics, and the deterministic model. So I think clarifying this difference is important, because, by identifying the type of model that we need to use, we can identify the related theory, so that we can study only the theory that is interesting to us. So basically, let me spend a couple of minutes. As I said, classic approach it's on the one hand deterministic model, on the other hand the probabilistic model. So what is the meaning of these two terms? And there are links here in this page to define what is the meaning of deterministic and what is the meaning of probabilistic. So the deterministic model is a model that to a given input assigns a unique output through an analytical relationship. So the definition is that in a deterministic model, a unique output is associated to a given input through an analytical relationship. So if I say that, for instance, Qt is equal to a coefficient phi times a rainfall over the catchment at the same time, this is deterministic, because if I fix rainfall, so if I fix the input and phi is constant and given, I get a unique output. And indeed, this is a kind of model that, let's say that I need to define what is RT in order to make this model understandable to you. RT is rainfall intensity per unit area. Rainfall intensity times the area. So basically RT is rainfall intensity, let's call it IT times the area of the catchment. So this is a model that is widely used, and it's called the rational formula. We will talk about this model later. The rational formula. By the way, this is considered to be the first hydrological model proposed, and it dates back to 1859. Was proposed by an Irish scientist, and there is indeed, the model is very rational, because it assumes that the river flow is originated by rainfall, So if you know the rainfall that originates the peak flow, then you multiply the rainfall intensity at the same time, and this is an assumption, because you may say, yes, but sometimes the watershed reacts with a time lag. This is an assumption. You take the rainfall at the same time, you multiply it by the area of the catchment, and then you take a reduction coefficient. The reduction coefficient is called runoff coefficient. We will talk about the rational formula later, as I said. If the runoff coefficient and takes into account the water that is lost by evaporation, by infiltration. So basically, this model is very rational because the assumptions are reasonable. This model, once that you fix rainfall, gives to you a fixed value of runoff, of river flow. And if you have another event with the same rainfall, this model gives to you the same amount of river flow, which is something that you understand is not really appropriate, because you understand that the same catchment, if you get twice the same rainfall, will not deliver the same river flow. Why is that? Because maybe that evaporation was different, maybe that in the underground something different occurred, maybe that the initial condition of the catchment were different. So let's suppose that rainfall falls over the wet. You know that we say there is a proverb which says it rains over the wet, which means that it's much more impacting. If it rains over the dry, it's less impacting because the catchment delivers less water. So it doesn't take into account this. So this kind of model, you understand that it's something, it's a deterministic model. I mean, the same rainfall gives rise to the same river flow. And this is the concept that I want to stress. This is a deterministic model. There is no uncertainty. You see that the estimate is a number, no uncertainty. What is a probabilistic model? Let me take a break, okay? Because I understand that after 1 hour and a half, it is, something.